Hey, welcome back to Stoichiometry/Solutions Part 2, where we're going to go over limiting reactant, percent yield, and solutions. So let's start with a review question from last lesson, and I would recommend you pause the video and try it on your own, but I'm going to go over it. We're asked how much CH4 remains after 10 grams of CH4 reacts completely with 15 grams of O2 according to the following equation. So we're given an equation and it looks like it's balanced, so we don't have to do that. And we know that 15 grams of oxygen is going to be completely used. Alright, so the first thing I want to do here is convert these grams into moles. So 10 grams of, I don't like this color. Let me use black. Okay, so 10 grams of CH4, the molar mass is going to be 12 plus 4, so it's going to be 10 over 16. That's the moles of CH4. And to find of oxygen, you just do 15 divided by 2 times 16, 16 being the molar mass of oxygen. And so you get 15 over 32 for oxygen. Okay, so now that we have that, we know that CH4 and oxygen are in a 1 to 2 ratio. So that means if we know that 15 over 32 moles of oxygen are going to be completely used, let's calculate how many moles of carbon that is, of methane, CH4 that is. So we know that we're going to use 15 over 32 O2, and then we need to figure out x. So 2x equals 15 over 32 divided by 2. X equals 15 over 64 moles, that is. So when you use 15 grams of oxygen, you need 15 over 64 moles of CH4. And so how much CH4 is left? Well, we know that the moles of CH4 that we have is 10 over 16, which we found out over here. And we know that we need to use 15 over 64. And if we just do a bit of math, it's 40 minus 15 over 64, 25 over 64. We have 25 over 64 moles of CH4 remaining. And so how many grams is that? 25 over 64 times, if we multiply by molar mass, we get the moles, and if we multiply by molar mass, we get the grams, sorry. And we know that the molar mass is 16, we calculated that before. And you just do a bit of crossing out, 25 over 4, which is 6.25 grams of CH4. And that's your answer. The reason I started out with this problem is because it shows the idea of a limiting reactant very well. Sometimes it's also called a limiting reagent, so they're kind of interchangeable. I might use them interchangeably. But what this shows right here is that you could have many more grams of CH4, but if you don't have the oxygen, you're never going to get this reaction to happen. So we see that there's 15 grams of oxygen being used, but only what, 3.75 grams of the CH4 is actually used. So you could add tons of CH4 into the system and you won't get more products because you just don't have enough oxygen. And that is the fundamental idea of a limiting reactant. It's the reactant that runs out first during a chemical reaction. My thing is blocking it again. Okay. And a very common analogy is a bike. Let's say you have 40 wheels, right? 40 wheels could make 20 bikes, but let's say you only have 5 frames. You need a frame per bike, so it doesn't matter how many wheels you have. The limiting reactant here is the frame. You would need more frames. If you have 5 frames to 40 wheels, you still need more frames to create more bikes. And that's how chemical equations and reactions work. So to calculate which compound is going to be the limiting reactant, there are usually two methods for this. The first method is comparing the moles of reactants. First step of that is to calculate the number of moles of each reactant and determine how many moles of one reactant you need to fully react with all the moles of the other reactants. It's hard to see how all this makes sense without doing a problem first. So let's take a look at this problem. 18.1 grams of NH3 is reacted with 90.4 grams of copper oxide. Determine the limiting reactant. So we're given the chemical equation here, and I'm kind of noticing off the bat that it's not balanced. So let's just quickly balance it. Looks like there should be a 2 here. 3. 3. And 3. Does that look good? 2 nitrogen, 6 hydrogen, 3 copper, 3 oxygen. That looks good. Okay. So let's do the first step. Calculate the number of moles of each reactant. We have 18.1 grams of NH3, and the molar mass of NH3 is 17, and that's going to be about 1.06 moles. On the other hand, copper oxide is, we have 80 what? 80 something? 90.4, 90.4 grams of copper oxide, and the molar mass for that is going to be right about 80 grams. And that's going to get you about 1.13 moles. Okay, so let's look at step 2. Determine how many moles of one reactant you need to fully react with all the moles of the other reactants. So what it's saying here is that with this many moles of NH3, how many moles of copper oxide do you need to fully react this? So we know that that the ammonia and the copper oxide are in a 2:3 ratio, and we have 1.06 moles of the NH3. So how many moles of copper oxide are there? Copper oxide is it going to be? So let's do the math. 3.18 equals 2x. And so x is going to equal 1.59 moles. What that 1.59 moles means is that with 1.06 moles of ammonia, we could technically make 1.59 moles of copper oxide. But we don't have 1.59, we have 1.13. And since the amount we can make is greater than the amount we have, that means copper oxide has to be the limiting reactant. And so what you did here was that you compared the values. You compared how much you could make with one reactant. And if it's more than the amount of reactant that we do have, that means the reactant that we have less of is the limiting reactant. And so let's look at the second method of calculating the limiting reactant. The second method involves comparing the amounts of products that can be produced. So the first step is going to be the same. It's going to be calculating the number of moles of each reactant, but the second step is a little different, because now you take the moles of product, you determine the moles of product you could make with the moles of each reactant that you have. So again, let's look at a practice problem. Well, it's the same one actually. Okay, so I balanced it and did the first step, but now we change up the steps from the previous method. Let's calculate, let's pick a random product. Let's say we'll take nitrogen gas. So with 1.06 moles of NH3, how much nitrogen gas could I make? Well, ammonia to nitrogen gas is in a 2:1 ratio. So if you find x here, x is going to be 0.53. Let me erase that. 0.53 moles. Okay, so with 1.06 moles of NH3, you can make 0.53 moles of nitrogen. Let's calculate the same thing for copper oxide. Copper oxide is in a 3 to 1 ratio. So 1.13 divided by x. And so that's going to be... Okay, so x is going to equal 0.377 moles of N2 gas. What we see here is that the ammonia can make more nitrogen gas than the copper oxide, and that means that the copper oxide is going to be the limiting reactant. With the amount that you have, you can make less. And that is the definition of a limiting reactant. So again, we got that copper oxide is the limiting reactant. You can use either method that you like. It doesn't really matter which one you use, but make sure, like, it's kind of easy to mess up on some of these, so make sure you take your time and go slow and carefully. Okay, let's look at a practice problem from the test. In the diagram above, the paired open spheres represent H2 molecules and the paired solid spheres represent N2 molecules. When the molecules in the box react to form the maximum possible amount of ammonia molecules, what is the limiting reactant and how many molecules of NH3 can be formed? Okay, so first of all, let's write out the reaction here, right? It's going to be H2 plus N2, and that forms NH3. And let's balance it. So add a 2 here, add a 3 here. All right, now let's count up the number of molecules that we have. We have 5 and 2 molecules, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogen molecules. Okay, so let's go with the second method where we take the number of reactants and then see how much product it can make and then compare those values. So 5 nitrogen molecules can create 10 NH3 molecules, and 12 hydrogen molecules can create 8 nitrogen molecules. And what do we see here? The hydrogen creates less, and therefore the hydrogen is going to be the limiting reactant. But that's not all the question asks. It also asks, and how many molecules of NH3 can be formed? Well, I guess we just calculated that here. So it's 8 NH3 molecules. And that's because hydrogen is in a 3 to 2 ratio. So if you have 12, you're going to need 8. So you have 8 molecules of NH3. So the answer to this question is that H2 is the limiting reactant, and you can make 8 ammonias with that amount. Okay, so everything that we've basically been dealing with here is theoretical yield, which is the maximum amount of product that can be formed when the limiting reactant is fully consumed. But that's not what happens a lot of the times. 100% is theoretical yield, but percent yield is the percent ratio of the actual yield to the theoretical yield. So in theoretical yield, let's say you were expecting to make 100 kilograms of something, but you actually made 87 kilograms of that same thing. So your percent yield is 87%. And percent yield can never be over 100%. 100% is very hard to get, but over 100%, that cannot be true. And if you do get 100% yield, then you probably messed up somewhere. I think the best way to practice this theoretical yield stuff is just going into a problem. And we have this very daunting problem here that says aspirin C9HA04 is prepared by the acetation of salicylic acid C7H6O3 according to the following equation, etc. If the yield of this reaction is 83%, what mass of salicylic acid would be required to prepare 1 kilogram of aspirin? Okay, so we know that the yield of the reaction was 83%, and that yielded a kilogram. So how much was really used in the process. So if 0.83 of the original amount is left, and apparently that creates a kilogram, which is 1,000 grams, how much was the original mass that was used in the reaction? And we can find that out by simply dividing. And x is going to be around, let me do the math, 1,204 grams. Remember, this is the mass of aspirin. So we prepared a thousand grams of aspirin, but at only an 83% yield, you would need 1,204 grams of aspirin to get that 1 kilogram. Now we need to convert this many grams of aspirin to salicylic acid. And the way we can do that is by comparing the ratios again. So salicylic acid, which is this, and aspirin, which is this, are in a 1-to-1 ratio. I don't want to write out the equation, but they're in a 1-to-1 ratio. That means so the number of moles of aspirin is going to equal the number of moles of salicylic acid. Since we know the mass of the aspirin, we can easily calculate the moles. We just divide that by the molar mass, and we can find out the molar mass by just 9 times 12 plus 8 plus 16 times 4, and that's going to give you 180. So if you divide 1,204 divided by 180, you're going to get that you're going to have 6.69 moles of aspirin. And remember, since aspirin and salicylic acid are in a 1-to-1 ratio, that means you're also going to have 6.69 moles of salicylic acid. How do I spell it? C-Y-L-I-C. Acid. Okay. The question asks what's the mass, so we can easily determine the mass by just multiplying 6.69 times the molar mass. And the molar mass is going to be 7 times 12 plus 6 plus 3 times 16. And that is going to equal 138. So 6.69 times 138 equals 623 grams. So the mass of the salicylic acid required to prepare 1 kilogram of aspirin is 923 grams. And if you're wondering what the answer was on like the actual test where you had multiple choice answers, it was 0.92 kilograms. So yeah, it took it in kilograms, but we just use grams. But really, the thing to understand here is that percent yield is a measure of how much was actually prepared versus how much was used in the process. So we found out that 1,204 grams of aspirin was used, but only 1 kilogram was produced. Let's move on to solutions. And a solution is a homogeneous mixture where a substance called the solute is dissolved in another substance known as the solvent. A homogeneous mixture just means that if you were to like look at the mixture, you wouldn't be able to tell the distinct parts of the mixture. And there are specific, we come back to these specific properties of solutions, which is molality and molarity. And molarity is the one used most often, and it's the moles of solute per liter of solution, but molality is also somewhat helpful, and that it describes moles of solute per kilogram of solvent. And it's very important to remember molarity is big M and molality is small m. I hope you don't forget. And let's do another practice problem, because it's like really the only way to get it down. What mass of NaOH is contained in 250 mils of a 0.4 molar sodium hydroxide solution. Okay, so we have NaOH, we have 250 mil, and 0.400 molar solution. Let's dissect what this 0.4 molar solution means. It means in 1 liter of the solution, you're going to have 0.4 moles of the solute. And the solute in this case is the NaOH. So if we know that in 1 liter there's 4 moles, how many moles are going to be in 250 mils or 0.25 liters? And you can do the math, and it's going to come out to 0.1 moles. So in a 250 mil solution of 0.4 molar sodium hydroxide, you're going to have 0.1 mole of sodium hydroxide. And if we're asked to find the mass, all we need to do is multiply the number of moles by the molar mass. So 0.1 times molar mass of NaOH comes out to about 40 grams. So the mass of the NaOH contained in this solution is about 4 grams. Again, the important thing is this 4 molarity that we saw here. The molarity just means 0.4 moles in a 1 liter solution. And then you can dissect that. You can say if there's 0.4 moles in 1 liter, how many moles are there going to be in 0.25 liters? And that's exactly what we did. Another important part of solution stoichiometry is a dilution, which is the process of decreasing the concentration of a solute in a solution. So if you were like in a lab and you wanted, I don't know, 0.25 molar hydrochloric acid solution, you're probably not going to find bottles lying around with 0.25, with 0.5, with 1, with 2. What you're going to find is probably one stock solution, and it's up to you to dilute it to get the concentration that you like. And thankfully, it's pretty easy to dilute using this formula. M1V1 equals M2V2. And people use people say move to remember it. It just means the molarity times the volume of the initial concentration, and then it's going to equal the molarity times the volume of the end solution. So let's look at an example. How many milliliters of 0.5 molar copper sulfate solution must be added to 160 milliliters of water to achieve a 0.3 molar copper sulfate solution? So we're given that M1, the initial molarity is 5 molar. And we don't know the volume because we're asked to find how many milliliters of it. That's the initial volume. And we can just symbolize that as X. M2, we know that M2 is going to be 0.3 molar because that's the end concentration that we want. And V2, we know that 160 milliliters of water was added. And a common mistake here would be to just say 160 here. But what's going on is that the 160 ml of water is going to be combined with the initial volume of X. So you need to combine them instead of keeping them separate. So the end volume isn't 160, it's 160 plus X. And then if we just plug this in, and solve for X, we are going to get let me do the math. That the initial solution that was added is about 10.2 milliliters. So 10.2 milliliters of 5 molar copper sulfate solution must have been added. And that is how you calculate it. So the big takeaway here is that the second volume is to be added. So you have two solutions being combined. So you don't want the volume of one or the other, you want the volume of them both. So make sure you include that in your calculations. We are almost done for this lesson. We just have a couple more practice problems. And if you want to pause and try these on your own, please feel free to. A reaction mixture is prepared containing zero point 0.6 mole of aluminum and 1.2 moles of manganese dioxide. The mixture is heated until one of the reactants has been completely consumed according to the equation blah blah blah. What quantity of which reactant remains uncombined? Okay, so this is a classic limiting reactant question, and then after we find the limiting reactant, we find out how much of it is uncombined. So let's do the strategy where we figure out how much product a certain reactant can make. So with 0.6 mole of aluminum, you're going to be able to make 0.3 moles of aluminum oxide. Okay, and let's look at the manganese. So 1.2 mole of manganese, MnO2, sorry, is gonna be able to create 0.4 moles of aluminum oxide. And remember, this is just because aluminum to aluminum oxide is a 2 to 1. So if you have 0.6, you're going to need 0.3. And in this one, it's a 3 to 1. So with 1.2, you need 0.4. What we see here is that aluminum has to be the limiting reactant because it creates the least product. And so if aluminum is the limiting reactant, that means manganese oxide is the one that's going to remain uncombined. MnO2 remains uncombined, but how much? Well, now we can compare the reactants, right? With 0.6 moles of aluminum, how many moles of manganese is that? Well, let's just say it's X moles of manganese oxide, and we know that the ratio between them is 2 to 3. So if we do the math, zero 0.9 moles. If you had 0.6 moles of aluminum, you would use up 0.9 moles of manganese oxide. And since you have 1.2 and you only use 0.9, you're going to have 0.3 moles remaining. So manganese oxide is remaining, and 0.3 moles of it is the amount that's remaining. I like this question because it combined the product method that we use, and then it also made us use the reactant method that we also mentioned. All right, let's look at the second one. Phosphoric acid can be manufactured according to the following reaction. Big reaction. If equal masses of calcium phosphate, molar mass 310, and silica, molar mass 60. Also, it's important to mention that on this test, molar mass is referred to as capital M. So don't get it confused with molarity. And silica are reacted with excess carbon, oxygen, and water to produce 1,000 kilograms of phosphoric acid, molar mass 98 grams. What mass of calcium phosphate was used, assuming 100% yield? Okay, so let's use the information that we know. We know that we have 1,000 kilograms of phosphoric acid. And we can manipulate this number to get us the number of moles of phosphoric acid. So 1,000 kilograms is going to be 1,000,000 grams. And if we divide by the molar mass, we're going to get that we have 10,204 moles of phosphoric acid. Now, what we could do here is just convert the number of moles of phosphoric acid to the moles of calcium phosphate. But the problem with that is that we don't know if calcium phosphate is going to be the limiting reactant, or if silica oxide is going to be or if silica is going to be the limiting reactant, because we're told that they have the same masses. So we're going to have to make sure that that we get the right limiting reactant. So with 10,204 moles of phosphoric acid, we are going to be able to make 5,102 moles of calcium phosphate. And that is also going to be able to create 15,306 moles of silica. Silica is SiO2. Now we can turn these into grams, because we know that they have the same amount of grams. So if we take the one with the largest mass and we use that mass as the same mass that both have, then we know that we will be able to fully go through the reaction and produce the 1,000 kilograms of phosphoric acid that we need. So 5,102 moles times 310, that's going to be a big number, 1581620 grams. While this one is going to be 15306 times 60, which is also a big number, but it's not as big. 60 grams. So the number that we go with here has to be the bigger number, because with the bigger number, we are sure that we won't run into any problems being able to produce the 1 kilograms of phosphoric acid that we need. And therefore, this is how much calcium phosphate we need to use to produce 1,000 kilograms of phosphoric acid. Obviously, this is not the number that like is on the answer sheet. I think on the answer sheet it's like 1,580 kilograms, but we did in grams, so yeah. On the test, you would probably just answer this, but it's cool to see how we got all this. All right, last one. Permanganate ion oxidizes hydrogen peroxide in acidic solution according to the following equation. Big equation. If 35 ml of an acidic 0.15 molar potassium permanganate, I think that's the name for it, solution is required to consume all of the H2O2 in a 50 ml of a disinfectant solution, what is the concentration of the H2O2 in the disinfectant? Okay, so let's use the information that we are given. 35 ml, and that's at 1.50 molarity. What we can take from this information is the number of moles of permanganate ion. We can take the number of moles of that, and that is helpful because we can relate that number to the number of of H2O2, because we know that they're going to be in a 2:5 ratio. So if we find the number of moles and we multiply that by 5/2, we can get the number of moles of H2O2. So let's try doing that. 0.15 molarity means 0.150 moles per 1 liter, which if we want 35 mils or 0.035 liters over X, that means we have 0.00525 moles of permanganate ion. And so now we need to relate that to H2O2. We know that permanganate ion and H2O2 are in a 2:5 ratio. 904 minus over 5 H2O2. So if we have this many moles of uh, permanganate ion, that means we're going to have, how much is that? 0.013125. We're going to have this many moles of H2O2. And what we need to do with that is find the concentration, right? We know that it's going to be a 50 ml solution, and let's say the concentration is xm, x molar. We know that there's going to be x moles in a 1 liter solution, and we know that in a 50 milliliter solution, or 0.050 liter solution, there's going to be 0.013125 moles. And using this information, we can determine the molarity. Let me just do that real quick. And the molarity is 0.2625. I think on the answer sheet it's 0.263 molar. And that is the answer. So let's review what we did in this question, right? We took the milliliters and the molarity that were given to find the number of moles of permanganate ion. We used that the number of moles, to relate that to the number of moles of H2O2 that we need. Once we found the number of moles of H2O2, which is this number right here, we know that in 50 milliliter solution, there's going to be that many moles. So how many moles are going to be in a 1 liter solution? And you can set up the proportion to figure that out. And we figured out that it's going to be a 0.263 molar solution. And that's it. That's all I have for this lesson. I'll see you next time for part 3.